Okay, Sharif, Assalamu alaikum. So inshallah today we'll be continuing the process of learning how to use the steam table and also refrigeration table. So as we talked last time, we do have tables for a steam, 3 tables for a steam based on actually the saturation curve for the phase exchange process. We do have subcooled zone, we do have saturation zone, and we do have the superheated zone. Also, we do have refrigerant table or refrigerant for one of the refrigerant, which is 134A. We do have tables also for this refrigerant, which has been used actually, or it is used most probably in many refrigeration and air conditioning cycle. The procedure how to use a steam table are typically the same as the procedure for using the refrigeration table. So we'll just introduce the process how to use the steam table, and then actually same procedure can be applied for the refrigeration table. We do have for steam table, we do have saturated table, the saturation table. We do have table A4 and also table A5. Table A4, as we said, if temperature is given, and table A5 actually is used if the pressure is given. So if temperature is given, just to go and use table A4. Pressure is given, just use table A5. We do have also the superheated table. Superheated table in the superheated zone, which is table actually A6, and also we do have the subcooled or compressed liquid tables, which are actually we do have table A7. In case of refrigerant 134A, instead of table A4 and A5, there will be actually table A11 and table A12. For the superheated zone, we do have table A13, and in subcooled zone, we do have actually no tables for this zone, as the saturation temperature for the refrigerant is very low, so we cannot find it, or we can find, but it is difficult to find actually refrigerant in the subcooled zone because it has very low saturation temperature. So usually it exists either in the saturated mixture zone or in the superheated zone. Let's look at this table. We looked last time at table A4, and we said actually in this table is starting with temperature, and at a given temperature the saturation pressure at this temperature is given, and also the saturated liquid and saturated vapor properties are given in this case. If you look at the saturation curve on the TV diagram, at a given temperature T, this point actually, or this line, the left hand side of this saturation curve represents saturated liquid. So all of the properties at given temperature at the intersection with the saturated liquid will have the suffix F, indicating the saturated liquid state. So properties actually at the intersection with saturated vapor line will have the suffix G, indicating actually the gas phase. So at a given temperature in this table, the saturated liquid properties will be given and saturated vapor properties will be given. So you will see here we do have a specific volume, V fluid, and also we do have a specific volume, V gas. Also in this table, those are actually the intensive properties, which is called also as the specific properties, which are actually the properties per unit mass. So this specific volume is actually the volume per unit mass, meter cube per kilogram. In this table also you will find U fluid and you will find U gas. Also you will find another parameter which is UFG, which is the difference between U fluid, U gas and U fluid. So the parameter UFG is just U gas minus U fluid. Also you will find in this table we do have enthalpy H fluid, and we do have also enthalpy H gas, and we do have the parameter HFG. You know enthalpy of a gas is equal, or any fluid actually, is equal to internal energy plus flow energy, and we do have this parameter HFG is just the difference H gas minus H fluid. The enthalpy and the internal energy in this table also are the specific properties calculated in kilojoule per kilogram. Okay. The unit for enthalpy and the internal energy is kilojoule per kilogram. HFG also, as it is actually representing the total energy of the flow, so this means actually from the saturated liquid to saturated vapor, this means HFG actually is equal to the latent heat of vaporization. So HFG, which is actually the difference between the saturated vapor enthalpy minus the enthalpy of saturated fluid. This difference actually represents the energy that has been added to this substance to convert from the liquid phase to the gaseous phase. It is called the latent heat of vaporization. Also you'll find here the entropy is fluid also entropy S gas, and the difference SFG, which is the difference between S gas minus S fluid. So we do have SFG is equal to also S gas minus S fluid. And the entropy, the specific entropy is calculated in kilojoule per kilogram Kelvin. It is also representing the specific property of this fluid. Okay, so in this case, if you do have the state of the substance is just saturated, he said actually the state of the substance is saturated liquid, so at this temperature, just to go to the table, then actually if the state is saturated liquid, then the specific volume will equal to what? V fluid. But if he said the state of the substance is saturated vapor, so this means actually the volume of the substance will equal to what? Will equal to V gas, and all actually other properties, internal energy will equal to U gas, and the enthalpy, and also the entropy in this case. Okay. Like, what if we do have actually a state here in between actually the liquid phase and the vapor phase? It's just a state in between here. So we do have a mixture of gas and fluid, and of liquid plus gas. In this case, we don't have only pure liquid or pure gas, just we do have a mixture in this case. So in this case, at this stage, we do have the volume is a specific volume V. Like when you go to the table at this temperature, you will find actually what is given is just V fluid, and also V gas is given. Like I need to calculate in this case the volume at this given state. So what should we do in this case? Let's look at the definition of this volume. Specific volume actually, not volume. Specific volume of this substance, of any substance, is equal to the total volume divided by mass. So we do have the specific volume V is equal to the total volume V total divided by the total mass. We do have at this point, we do have mixture plus gas plus fluid. So it will equal to the volume of fluid plus the volume of gas. This is the total volume divided by the mass of fluid plus mass of what? Plus mass of gas. Just divide this term, so it will equal to volume V fluid divided by mass fluid plus mass of gas, plus volume V gas divided by the total mass, which is mass of fluid plus mass of gas. Okay? And look at this term. Look at this term first. If I multiply it by mass of gas and divided by mass of gas. So in this case, mass of gas divided by total mass. This represents actually the quality of the mixture X. Quality of the mixture is the mass of gas divided by the total mass. And this term is the volume of gas divided by the mass of gas. It should represent the specific volume V gas. Okay? So this term, all of this term, we can just represent this term to be equal to the quality of the mixture X multiplied by specific volume V gas. Same here, if we just here multiply by mass of fluid and divide also by mass of fluid. Okay? So in this case, we do have V fluid, volume of the fluid divided by mass of the fluid should represent the specific volume V fluid. And we do have mass of fluid divided by the total mass. We do have mass of gas divided by the total mass is X. By mass of fluid is equal to the total mass minus mass of gas. So it will equal to, just add here mass of fluid, just add plus mass of gas minus mass of gas. Okay? Mass of fluid plus mass of gas divided by mass of fluid plus mass of gas, this should represent 1. Minus mass of gas divided by the total mass, which should be X. So this term will be 1 minus X. So the whole of this term can be represented by V fluid multiplied by 1 minus X. And in this case, we can say the specific volume at this given state will equal to what? V fluid multiplied by 1 minus the quality of the mixture X plus V gas multiplied by the quality of the mixture X, which should equal to V fluid plus take the quality X common, so it will be V gas minus V fluid. Or a specific volume will equal to V fluid plus the quality of the mixture X multiplied by V gas minus V fluid. So at a given temperature, I will go to the table. In this case, I can get V fluid, and I can also get V gas at this temperature. And we do have the quality of the mixture, then we can calculate what the volume at a given state of a mixture of liquid plus gas. Actually, very similar to this procedure, we can calculate also the internal energy will equal to U fluid plus X multiplied by U gas minus U fluid, which is called as UFG. And also the enthalpy will equal to U fluid plus X multiplied by HFG. Entropy also is similar, S fluid plus X multiplied by SFG. So to calculate the properties in the table, I will be using the table to get the saturated liquid and saturated vapor properties. Then I will be calculating the properties using actually those relation between V fluid, V gas, and the quality of the mixture to calculate the total property of a given substance. So in this case, what will be given for you and what are the procedures that we should follow in this case? Let's look here. What will be given for you in this case is pressure or temperature with one specific property. As we said, in the saturation mixture zone, all point actually in the saturated mixture has the same pressure, same temperature. So pressure and temperature are not independent properties. And to use the table, actually you have to have two independent and intensive properties. So if pressure and temperature are given, so it should be the state is not actually saturated. We are not in the saturation mixture zone. So to be in the saturation mixture zone, either actually pressure or temperature will be given with one of the specific properties. Maybe specific volume is given, maybe internal energy, maybe enthalpy, or maybe actually the entropy of the fluid. So in this case, either pressure or temperature will be given with one of those specific properties. This property or this property or this property. So let's say, anyway, either pressure, let's say pressure and the specific volume are given in this case. So in this case, I will be going first to the saturation table. If pressure is given, I will be going to the saturation table, either table A4 or table A5. Table A4, if temperature is given, I will be going to table A5 if pressure actually is given in this case. If pressure is given, then we can use table A5. If temperature is given, I will be using table A4. And from this table, I can get actually V fluid, I can get V gas, U fluid, U gas, H fluid, H gas, S fluid, S gas. Actually, you will not need actually to get all of the properties, but depending on the given property. If the given property is volume, then I will get V fluid and V gas. If the property is internal energy or enthalpy, I will be getting actually internal energy, U fluid, U gas, or H fluid, H gas, or even S fluid, S gas. But let's say volume is given, so I will get actually V fluid from the table and V gas. Then actually I will be comparing those values with the given specific volume. So in this case, first case, if we find actually the specific volume that is given is greater than V fluid and less than V gas, so this means we are inside the saturation zone. This is the saturation curve, and this is at the temperature, this is V fluid, and this should be V gas. If V is between V fluid and V gas, so we are in the saturation zone. So in this case, the state of the substance is we do have saturated mixture, and in this zone actually we do have the temperature will equal to what? This given temperature, or at, let's say at a given pressure, I go to table A5, then I will get actually also the temperature, which is the saturation temperature. If I'm going with temperature, I will be getting actually the saturation pressure. So in this case, the temperature will equal to T saturation, and the pressure will equal to B saturation. And in this case, the next step is to calculate what? Is to calculate the quality of the mixture X. In this case, actually, we are given a specific volume is given. And we do have V fluid and V gas, and we said V is equal to V fluid plus X multiplied by V gas minus V fluid. From this relation, we can get the quality of the mixture X will equal to V minus V fluid divided by V gas minus V fluid. Okay? Now we have calculated X. Then if I need actually to calculate the internal energy, calculate enthalpy or entropy, then in this case I got from the table U fluid, U gas, then we can just substitute U will equal to U fluid plus the X that we have calculated multiplied by UFG. H will equal to H fluid plus X multiplied by HFG, and also entropy, if I need to calculate, will equal to S fluid plus X multiplied by SFG. So in this case, we have calculated X, and then we can calculate the other properties in this case. طيب, if while I'm checking actually V and I found between V fluid and V gas, so those are the procedure. But if you find actually this specific volume V is just greater than V gas, so this means actually we are in what? In the superheated zone. But if V is less than V fluid, so we are where? In the subcooled zone. But let's look at actually those zones and how we use actually those tables. So the subcooled or compressed liquid table. Subcooled or compressed liquid table, which is actually table A7 for steam in this case. So in this table actually, if we are in the subcooled zone, this means actually the temperature is less than the saturation temperature. Or in this zone actually the pressure is greater than what? Is greater than B saturation. How come? If you look here on the PV diagram, okay, this is actually the saturation curve. At a given temperature here on the TV diagram, so this line actually should be presenting, this line presenting, horizontal line representing constant temperature, and this line should be presenting actually the saturation pressure at this given temperature. So at a given temperature T, the only way actually to have pressure greater than the saturation pressure at this temperature is actually in the subcooled zone. So in this case, the pressure at any point here, you can represent actually this pressure line at this point. This pressure will be greater than what? Greater than the saturation pressure at this given temperature. So at any point here, you will find actually the pressure is just greater than the saturation pressure. So this means we are in the subcooled zone. So at a given temperature, this is actually T is less than T saturation at a given pressure, or B is greater than B saturation at a given temperature. So at a given temperature, if pressure is greater than B saturation, this means we are in the subcooled zone. But at this given temperature, if you look at actually any point here in the superheated zone, the line actually of pressure, this pressure is less than B saturation. So at a given temperature, if P is greater than B saturation, so we are in the subcooled region. If it is less than B saturation, so we are in the superheated zone. So for the compressed liquid table, the temperature should be less than also to be in the subcooled zone. The temperature should be less than actually the saturation temperature. And also in this case, the specific volume should be less than what? Less than V fluid, okay? So in this zone, at any point here, the specific volume should be less than V fluid. And also the internal energy should be less than U fluid, and sub B is less than H fluid, and also the entropy is less than S fluid, okay? And in this case, we have to use actually table A7. If you look at table A7 is just divided to sub-tables, a set of sub-tables. Each table actually is existing at a given pressure, and at a given for a range actually of temperature, they give the properties including specific volume, internal energy, enthalpy, and entropy. All of these properties are given. So if pressure and temperature are given, so I will locate the exact table at actually this given pressure, go to this table at this pressure value, and at a given temperature, then you will actually specify this temperature, and then you can get the other properties, okay? Like this is in case if we are in the subcooled region. So in this case, as we said, we have to use table A7 in this case, okay? Like in the superheated zone, which is actually the table that we are left with, for the superheated zone, or superheated table, which is table actually A6. The condition actually to be in the superheated zone is that the temperature is greater than the saturation temperature at a given pressure. So at a given pressure, line saturation pressure, to be actually in the superheated zone, the temperature is greater than the saturation temperature at a given pressure. Or pressure is less than what? less than the saturation pressure at a given temperature, because either the temperature or pressure will be given. So at a given pressure, if the pressure is given, I will check actually with the saturation temperature from the table and compare it with the given value. If the given value is greater than the saturation at this given pressure, so this means we are in the superheated zone. Or pressure less than V saturation, or we do have a specific volume is greater than V gas, internal energy is greater than U gas, enthalpy is greater than H gas, and also we do have entropy is greater than also S gas. So all of these conditions says actually that we are in the superheated zone, and in this case actually we have to use table A6. Table A6 is exactly similar to the table actually A7. We do have also set of subtables. Each table is existing at a given pressure. So in this case, if pressure and temperature are given, so I will go and locate actually the exact table at this given pressure, and at the given temperature we can locate the other properties. Okay. Right. Let's check here. By this actually we are done with the different table for steam. Those are actually table A4, A5, A6, A7 for steam table. Exactly the same procedure are applied for refrigeration table, but we do have different table number. We do have, instead of table A4 and 5, we have 11 and 12, and instead of table A6 we do have table A13. Okay. Right, let's look at actually the steps how to use a steam table. So how to use a steam table. Okay, so the steps how to use tables in general. You will apply the steps actually to steam table, and then you can apply the same procedure for refrigeration table. We do have actually different cases. Let's start with case A. In this case actually, what will be given for you, either pressure or temperature is given, plus one of the specific properties, either V, internal energy, enthalpy, or entropy is given. Okay, so either of these properties will be given, pressure or temperature, plus one of these properties, a specific volume, internal energy, enthalpy or entropy is also given in this case. So the first step actually that you should do, I will be going to table, either table A4 or table A5. Table A4, as we said, if the temperature is given, table A5 if pressure is given. Then in this case, I will be getting, let's say, specific volume is given. Let's consider this case. I will get actually in this case V fluid, and also I will get V gas. Okay? So either pressure or temperature are given with one of the specific properties. Just to go to table A4 or A5, get this specific property, saturated liquid property and saturated gas property. And then compare those values actually with the given value. So step one, I will be considering actually if a specific volume is given, and then if other property is given, same procedure are applied. So in this case, if we find V is greater than V fluid and less than actually V gas, then in this case, the state of the substance is saturated mixture. And in this case, the temperature is equal to the saturation temperature, and the pressure at this state is equal to the saturation pressure. So if pressure is given, so this pressure is the saturation pressure. And from table A5, we can get the temperature. And the temperature in this case will equal to the saturation temperature. And in this case, the next step actually is to calculate X. And to calculate X, it will equal to V minus V fluid divided by VFG, which is V gas minus V fluid. The total volume V is given. V fluid and V gas will be just from the table. Then we can calculate actually the quality of the mixture X. Usually you will be in need, when you apply the first law of thermodynamics, you will be in need to calculate either the enthalpy or internal energy, or you may need actually to calculate also the entropy. So to calculate the other property, now we do have X. Then we can say internal energy will equal to U fluid plus X multiplied by UFG. And here from the table, you can get actually internal energy U fluid, and also you can get internal energy U gas, or you can directly get UFG. It is given in the table. So U fluid and UFG, then you can calculate U. Also like this in Salby will equal to H fluid plus X, HFG entropy will equal to S fluid plus X multiplied by SFG. And all of these saturated liquid and saturated gas properties can be just located from the table. And we do have the value of X is calculated. Type, this is actually the first option if V is greater than V fluid and less than V gas. Type, if we check actually, second option, if we find actually the specific volume is greater than V gas. So from table I got V gas and I'm giving V. If you find the given volume is greater than V gas, so the state of the substance in this case, in the superheated, we do have superheated vapor. This is the state of the substance. And in this case we have to use which table? Table A6. Okay? So from table A6, at this pressure, and given a specific volume, with this pressure you will locate actually the table at a given pressure, and then just to go through the specific volume until you reach your value, and then actually we can calculate from table A6, we can calculate the other properties which are actually the internal energy in Salby, and also we can calculate the entropy from this table. If you look at table A6, at this given pressure, you will be just here we do have temperature, V, U, H, and also you do have air entropy. So at this given pressure, just locate this table, and for the column of a specific volume I will go until actually I locate this value that is given, and then I can get actually the other properties, including internal energy and Salby entropy, and also the temperature if it is given. Okay, this is in case if V is greater than V gas. Type, if V option number, let's say option number 3 here, if I find actually V is less than V fluid. V is less than V fluid, so in this case the state of the substance is subcooled or compressed liquid. So in this case the state of the substance is subcooled or compressed liquid. And in this case I have to use table A7. So at this pressure and the specific volume or any other property, just to go to table A7 and I will locate actually those properties. Okay? And those are actually the first option if pressure or temperature are given with one of the specific properties. Type, let's go to the second option, option number B. In this case actually what will be given for you is pressure and temperature. So as pressure and temperature are given, so pressure and temperature are not actually independent in the saturation zone. So to use the table we have to have two independent and intensive properties. But pressure and temperature are not actually independent in the saturation zone. So this means if pressure and temperature are given, this means most probably you are not actually within the saturation zone. So the state should be either subcooled or superheated in this case. Okay? So the steps in this case if pressure and temperature are given, so I will be going either with pressure to table A5, then with this pressure from table A5 I can get what? The saturation temperature. And then compare this saturation temperature with the given temperature. So the first option, if we find that the given temperature is greater than the saturation temperature, so the state is what? Is superheated vapor. And in this case we have to use which table? Table A6 in this case. Okay? To calculate the other properties which are internal energy and Salby entropy, and also pressure is given in this case. Okay? Type, if state number 2, if you find the given temperature is less than the saturation temperature at this given pressure, so the state of the substance in this case is subcooled. And in this case we have to use which table? We have to use table A7 to calculate the internal energy and Salby entropy and the other properties. Type, in this case pressure and temperature are given. I took pressure and I went to table A5. Can I take temperature and go to table A4? Yes. So exactly the same procedure. So it's option for you. You can either follow this option Or you can just take this temperature and go to table actually A4. In this case, I will get the saturation pressure. Okay? So the first option, if you find actually the saturation pressure given is less than the saturation pressure, pressure less than the saturation pressure, so we are actually in the superheated zone, or actually the state of the substance is superheated table. So in this case I will be using table A6. Step 2, if you find actually this pressure is greater than the saturation pressure, so in this case actually the state of the substance is subcooled liquid or compressed liquid, and in this case we have to use actually table A7. But what you keep in mind actually is the temperature. Temperature greater than the saturation superheated. In the case of superheated, temperature is less than T saturation, the state is subcooled. Okay? So usually pressure is the reverse. So if less than B saturation, the state is what? Is superheated. If it is greater, the state is subcooled. And in this case I have to use actually table A7. You can follow actually either these steps or those steps if pressure and temperature are given, and this is actually should be state B. Okay, right, let's look at state C, another option also. In some cases actually you may find pressure and temperature also are given in this state, and you went actually to make this check and you find actually the state is subcooled. So you have made the check with pressure, I get the saturation temperature and compare, and I find the temperature is less than T saturation, and you find actually the state is subcooled or compressed. So in this case I have to use table A7. Okay? If you look at table A7, you'll find, we said this table is a set of top table. Each table is at a given pressure. You will find the first table or the first given pressure in table A7 is at 5 megapascal. So if the pressure is less than 5 megapascal, so we don't have table. We don't have subcooled table for the case of water. But if this is the case, I checked for pressure and temperature and I found the state is subcooled. But the pressure actually is less than 5 megapascal, so I don't have table in this case. So what should we do in this case? So in this case we assume actually the properties are equal to the saturated liquid property. So in this case we assume the specific volume V fluid, V will equal to V fluid at a given temperature, at the given temperature. And also internal energy will equal to U fluid at the given temperature. Enthalpy will equal to H fluid at the given temperature, also not given pressure, and the entropy will equal to S fluid at this given temperature. But why we take this assumption? Properties are equal to saturated liquid properties at this given temperature, not given pressure. Pressure is also given. So why don't we take, instead of going to table A4 at a given temperature, those are from table A4. All of these cases. Why not using table A5 at a given pressure and say specific volume is equal to V fluid at a given pressure? Let's look here. If we look at the saturation curve on the TV diagram, if we are in the subcooled zone at this zone, so actually this line should be representing this temperature, the temperature at this point. And at this point actually on the TV diagram, this line should be representing the pressure. And this is actually our state, subcooled. So the volume at this point, the actual volume should be this value. If I go to table A4 with this temperature, so I will get actually V, which is equal to, I said V will equal to V fluid. So this is the value, this is the value that we'll be getting actually from table A4. This is V fluid at a given temperature from table A4. But if I took the value at a given pressure, so this is the value V fluid that we'll be getting actually at a given pressure. So which one of them is closer to the actual value? This one, V fluid at a given one, at a given temperature. So in this case, if we don't have table, value is not listed in the table. Okay? Value is not listed, not actually value in between 2 points. In this case I can make interpolation. But I mean actually the table is not there. Pressure table is not there. So we cannot find the value listed in the table. Or we don't have table for this case. So in this case, we can use the assumption all properties will equal to the saturated liquid properties at the given temperature using table A4. This is actually because of the physics of the subcooled liquid. They are actually, the properties of the subcooled liquid are depending mainly on temperature more than actually depending on pressure. So if you do have actually pressure, if you actually the pressure is actually multiplied, let's say, by a factor of 100 or something. So in this case, actually, the change on the properties of the substance actually will be very minor. But if you do have a change in temperature, any change in temperature will result actually in a change of those properties of those substances. So if you do have liquid or something, if you apply very high pressure on this liquid or subcooled liquid, so in this case, the change of the properties will be very minor in this case. Okay. But for property like enthalpy, we do have enthalpy is equal to internal energy plus flow energy, BV. So enthalpy actually is function of pressure. So if pressure is increasing, the enthalpy will be changing. So this means this assumption is not that accurate. So in this case, actually, we can use this assumption. We can say enthalpy will equal to actually H fluid also, same as this assumption, to account for temperature, plus the specific volume actually V fluid at the given temperature also, multiplied actually by the difference of pressure, which is equal to pressure B, the given pressure, minus B saturation actually at the given temperature. Okay. So this will be actually enthalpy will equal to H fluid plus V fluid multiplied by the given pressure minus B saturation at the given temperature. So usually while using the table, the case will be actually, I will be considering H will equal to H fluid. This assumption will be valid while solving your problem or something, especially unless actually he asked you to calculate the exact equation to calculate the enthalpy. If he asked you to do this, just use this equation. If not, then we can use actually this assumption H is equal to H fluid. So we are left with only one notice for you regarding steam tables, which is the interpolation. If you went to the table, interpolation, if you went to the table, let's say, at a given temperature, I went to the table, I need to calculate, let's say, enthalpy, okay? So at a temperature T1, I find the enthalpy H1. And at a temperature, let's say, T2, the enthalpy H2. But I need actually the value at a temperature in between, I need to calculate the enthalpy H. So let's say the given temperature in the table is starting with 100, the second value on the table is, let's say, 200. And I need actually to calculate the temperature at 150 or 120 or something. I need to calculate the enthalpy. But actually this 120, this temperature is not there in the table. Just we do have 100 and 200. So in this case we have to make interpolation. So we can say T minus T1 divided by T2 minus T1, T minus T1 divided by T2 minus T1. This should equal to what? H minus H1 divided by H minus H1 divided by H2 minus H1. You do have T1, which is the value in the table, H1, T2, H2, and at a given temperature, which is given for you, I need to calculate H. So from this equation, I can calculate the value of H using interpolation. Okay. So that's all regarding the table for a steam table. For refrigeration table, actually, we do have the same procedures are applied, but instead of table A4 and A5, it will be A11 and A12. And instead of table A6, it will be table A13. Now, if we do have refrigerant with the subcooled zone, I have made the check and I find the status subcooled. So in this case, we don't have table. So in this case, we can apply the same assumptions that we have made for steam. We can assume all properties are equal to the saturated liquid properties, and we can continue the solution. Okay. So thank you.